And she will be telling us about her work on tensor networks for p-adic CFTs to, I can't read the rest of the title here.
Oh, you can't see the rest of the title. Oh,
let me just click here. Okay, to 1 + 1D real conformal field theories. So welcome, Janet.
that I'm talking about is something that we have been doing for quite a while with my collaborators, Wei, and our postdocs, and then subsequently with my student and is to try to look for tensor networks that describe, that reproduce features of the ADS-CFT correspondence. So clearly that is a very difficult task, and we started off with a toy model for ADS-CFT, the so-called p-adic, which I'll view in the first part of my talk, and go this and how that help us with looking for more realistic networks to work that reproduce might to so we haven't described three-dimensional CFTs do reproduce all the features some interesting things. So without further ado, let me just begin. So I'll start with talking about the p-adic tensor network looks like, so strange correlator. And as we're going to see, this is the tool, or this is going to be a way of. So I'll start with talking about the p-adic tensor network and some lessons that we have learned out of it. And we're going to see how some of the tensor networks that represent real CFTs, holographic tensor networks that represent real CFTs, and then we'll conclude our talk. So why I was obsessed with looking for holographic tensor networks? So I guess this audience already have some experience with this, but nonetheless, let me just say 2 words. The ADS-CFT correspondence suggests that the entanglement entropy of the CFT is related to the area of some minimal surface in the ADS bulk. And this picture seems to be very intriguingly similar to a tensor network representation of CFT ground states, notably the mirror type tensor network. If we want to compute the entanglement entropy of a region represented by a mirror type tensor network, then we can a very good estimate of the entanglement entropy would be the number of bonds that cut the minimal number of bonds that cut through the tensor network, which looks like a discretization of ADS space. And so this was an observation first made by Brian Swingle back in, I think, 2012. And so this motivated, this inspired people to look into tensor networks and see if it is, and in fact, it is providing a microscopic explanation of the ADS-CFT correspondence, whether we can, in particular, whether we could read off important aspects of the ADS-CFT dictionary from a tensor network reconstruction. If we're successful, then it would suggest that perhaps the tensor network is indeed providing a microscopic explanation of the correspondence. But of course, that is a very difficult task. We have to decide what is the, if we were to construct a tensor network, we have to construct a graph. We have to decide upon what values these tensors take. And if we were to read off any information about the bulk gravitational theory at all, with this bunch of numbers that defines the tensor networks, we have to define distances on this tensor network, and all of these things seems very difficult. So rather than working directly with the actual real CFT, we don't even know where to begin. We started with a toy version of the ADS CFT correspondence called the p-adic ADS CFT correspondence. The p-adic ADS CFT correspondence is a conjecture that generalizes the ADS CFT correspondence. What it says is that instead of considering a CFT in real space-time, what if the coordinates of the CFT is not a real number, but rather a p-adic number. So p-adic numbers are some different number fields that has a different notion of norms, which I'm not going to review here. What is important is that by considering these p-adic CFTs, you can look at their conformal symmetries in a very analogous manner as real CFT. And by looking into this conformal symmetry, how the conformal symmetry works, you can guess the dual geometry, which is whose isometry of this dual geometry is equivalent to the conformal symmetry of this p-adic CFT, and so that geometry would be a candidate as a dual to the CFT theory. And very fortunately, such a geometry is known to mathematicians, and so it was proposed by Gubser and collaborators that this geometry called the Broughart tree would be the ADS counterpart for p-adic or CFT. And since the Broughart tree is a discrete space, it has an asymptotic boundary, much like the ADS has an asymptotic boundary, and and the asymptotic boundary is a continuous space. Is not an important point. The important point is the tree itself is discrete, and so it is very suggestive that if I want to construct a tensor network describing the p-adic CFT, I might as well cover the tensor network on this Broughart tree. Exactly what we do, and if we do that, then there is no the construction is covariant. So to start with, there is no distinction between space and time. So you can think of this as a construction of, rather than the wave function of the p-adic CFT, we are constructing the partition function of the p-adic CFT. So in this partition function, so what should the tensors in this network take? So each vertex, we made a guess, we made a proposal for what these tensors should be, and we proposed that for every p-adic CFT, which is also characterized by primaries and their fusion coefficients, why don't we put these fusion coefficients, these structure constants of the p-adic CFT to cover every vertex of this holographic tensor network? And so therefore, every leg here would carry the labels of the primaries of the p-adic CFT. And we also weight every leg by some p to the delta. Delta is the conformal dimension of the primary, and p is a prime number that characterizes this p-adic field. The p in p-adic is a prime number. So we made a guess for these tensor for the values for these tensors, and there's an asymptotic boundary of this holographic tensor network. So you have to give a boundary condition for the dangling legs at the asymptotic boundary, and we propose, this is also a proposal, that we would project all the boundary legs to the identity element. So this 0 corresponds to the identity operator of the p-adic CFT. If I want to insert operators into the p-adic CFT, all I need to do is to replace the boundary point where the operator is inserted by the label corresponding to the primary operator. So suppose I want to do a 2-point function, I just replace two of the points at the boundary by the label corresponding to the boundary particular boundary operator. In which case, the tensor network would give you some number, and that number would match exactly with the expected 2-point correlation function of the p-adic CFT. Moreover, the contribution of the tensor network is such that actual contribution came from a fusion, a geodesic connecting the 2 points where you inserted an operator. This is not difficult to see because every vertex here, it corresponds to a fusion coefficient. Therefore, if I turn a particular boundary leg into a primary label and the rest of the legs remains identity label, then every vertex I would have identity fusing with this operator O, and so it would come back with O, and so all the non-trivial contribution would sweep out this unique geodesic that connects these two boundary points. So one extra interesting thing is that not only do the overall answer correspond
Sorry.
Yes.
Yes, Capelli, sorry, I think that if you don't explain what is a p-adic number and a p-adic conformal field theory, at least minimal amount of it, we will not be able to follow you at all.
Okay, but that would knock me a bit off course. So give me a moment and I will show you why, even without knowing what is a p-adic number, you would be able to get what I am about to say about real CFTs.
Especially a conformal field theory on a graph is something that really is not very easy to understand. So you have to define what you mean by conformal transformation on this. I mean,
okay. Let me see. I can let me say the following. So p-adic numbers. So p-adic numbers might sound a bit mysterious, but if I say X is a p-adic number, and I would say conformal transformation, let's say for simplicity, I have a one-dimensional CFT, so it is like a quantum mechanics, but it is one-dimensional, but time now is a p-adic number rather than a real number. Then how would I do a conformal transformation on this one-dimensional object? It would be ax plus b over cx plus d, except that I replace a, b, c, and d by p-adic numbers. Therefore, the conformal group for a one-dimensional p-adic CFT would be given by the so-called SL2QP, because the group is almost exactly the same as the real case conformal transformation A, B, C, and D by p-adic numbers. And so the two-point function would look almost like the usual two-point function of p-adic of usual CFT. It would look like something, if I have a two-point function, it would look like 1 over x1 minus x2 to the power 2 delta, except now x1 and x2 are p-adic numbers, and also the norm would not be a real norm. It would be a so-called p-adic norm. So these interesting details, but it doesn't really get into the structure of the tensor network. And I have a point to make about how to generalize this tensor network to real things. And if I go too much into the p-adic stuff, then I think you would not be able to see the connection, because I think some of these details of the p-adic CFT is not actually used in the construction of the tensor network and in the construction of tensor network for real CFTs. I hope this gives you a flavor of what p-adic CFT is. However, is that
yes, please go ahead.
So I'm sorry about not being able to give more details about the p-adic CFT, but the thing I want you to take home is that in this tensor network, you can recover not only in this tensor network, not only can you recover the two-point function of a p-adic CFT. I haven't written down what it is, but I wanted to say that in this construction, the way you get the answer is also important, because the way you get the answer tells you that it is the geodesic that is contributing. And more miraculously, the way that this geodesic contribute is such that it is in terms of a bulk boundary propagator on this graph. So in the original calculation of Gupso, when he proposed p-adic ADS-CFT, he computed the Klein-Gordon, he looked into the Klein-Gordon equation defined on this graph, and he solved for the Green's function of the Klein-Gordon equation on this graph. And the way this tensor network contributes is such that the numbers that came out of it in this fusion graph, because every vertex is a fusion vertex, because I propose that the vertex is given by the fusion coefficient of the p-adic CFT that I want to construct, it sweeps out a geodesic, and each vertex contributes exactly a factor that would end up leading to the graph Green's function of the Klein-Gordon equation on this graph. So not only I reproduce the CFT correlation functions, the way it reproduces it is such that there is some emergent Witten diagram that emerges on this graph. So we were also able to read off some Einstein equation out of a little bit away from a conformal geometry. And inspired by the usual ADS-CFT correspondence, the way we did it is to change boundary conditions that we put all the boundary legs to some linear combination of the entity that defining an RG flow. You can see that initially, if all the boundary conditions are 0, then 0 is a very, very special value. The identity operator is a special value in this tensor network, because every vertex you would have 2 zeros fused together, and 2 zeros would fuse to a 0. And so in the next layer, it is still 0 and 0 and 0 fused to 0 again. In other words, 0 is an eigenstate of this network, or 0 is a fixed point of this network. If the boundary is not a fixed point of this network, is not an eigenstate of this network, then in general, it would induce J and J would fuse to something else, and it would be a linear combination of lots of complicated things. If I fuse a linear combination of 0 plus some primary operator, it would fuse to some complicated things. And this complicated things in the next layer would fuse and goes to some other complicated things. So it gets more and more complicated at every layer that I fuse. And so a general boundary conditions that is not a fixed point of this fusion tensor network, or this RG tensor network, it would not define for you a conformal theory. This also makes a lot of intuition, makes a lot of physical sense. And this is going to be an important point that I am going to belabor upon when I talk about real CFTs. And so by changing boundary conditions so that it is no longer a fixed point of this tensor network, we would be able to define renormalization group flow for p-adic CFT. And from this non-trivial flow, we were able to read off an Einstein equation. Roughly, the idea was that we first have to define what it means by expectation value on this tensor network, expectation value for bulk operators on this tensor network. And the way we defined it is that since this is a fusion tensor network, we fuse an extra primary label onto a vertex using the fusion roots of the CFT. And if I fuse an extra thing here with fixed boundary conditions, what I'm going to get is another number. And if you look at this number, so if I don't have, if the boundary conditions are all 0, and if I fuse an extra primary here, you can easily check that the number I get would be 0, corresponding to the fact that all the bulk fields have 0 expectation value. But if the boundary is non-trivial, is no longer 0, but 0 plus some other things, then I would in general get a non-trivial value if I fuse an extra leg into a vertex. And if the boundary is close to 0, is 0 plus a little bit of some other things, then you can very easily check that the expectation value at any vertex would be given by the linear contribution of a linear term of the perturbation multiplied by a Green's function, which corresponds to a fusion line that came from the boundary to that feeds into these vertex, and then if you want to look at the quadratic contribution from the boundary, then you take two Green's function and connect it to a vertex. And so without an action, we reproduce the usual rules of the ADS-CFT correspondence with this proposal. Therefore, we believe that this proposal is sensible. And from there, we parameterize the distance of every edge. So before we put in non-trivial boundary conditions, all the edge are equivalent, very much like this is an isometry of this network. And so you can assign a distance 1 to every link on this network. When you change the boundary condition, clearly every layer becomes different. As we have seen, these boundary conditions are no longer fixed point of this tensor network, and it would appear like the bulk geometry has changed. And if that is the case, you have to assign distances to every edge, and we don't really know how to do that. And so we parameterize this. So assuming that we are only slightly perturbed away from the pure conformal geometry, the pure Broughart-Tizz tree, therefore every boundary is 0 plus a little bit of some other things. Then we work perturbatively in this little j. And we parameterize every edge by a power series in this J expansion. We parameterize the curvature of the graph in terms of edge distance perturbatively and as an expansion of J. And we also write down a stress energy tensor of the bulk that is an expansion in the bulk fields. And we find that the only way to fit the Einstein tensor in the bulk, which is we take it as an expansion of the edge lengths, and the bulk stress tensor, which we parameterize our unknowns in the expansion of phi, but phi, the expectation value of phi, is in turn in terms of, as we have seen, in terms of the boundary condition J as a power series expansion. We ask for if there is one way of fitting together this proposed Einstein tensor and stress tensor with lots of unknown coefficients. These A1, B, and C are all unknown coefficients in this expansion. And these H1s, R1s are also unknown coefficients. So there are lots of unknown coefficients. And the J itself, in terms of the boundary condition, is also full of unknown coefficients. But we constrain them by locality and rotational symmetry, but that's all the input we put in, and we ask if there's a way of fitting them together such that G plus T is equal to 0. So shockingly, because the ask a question. Yes, please.
Jane, so I want to ask, could you go back to your tensor network figure? So is each vertex a tensor?
Yes, every vertex is a tensor. In this graph, it will correspond to a 3-leg tensor.
So it doesn't have a physical index, right? Usually we have a tensor network, like for each spin it has a physical index, but in this figure, does it have a physical index?
Oh, okay, very good. So in case I go too fast here, as I mentioned, in this tensor network, we are trying to model the partition function of the CFT rather than the wave function of the CFT. The reason, right, and therefore we don't have physical legs, but we do have an asymptotic boundary in this geometry. And the asymptotic boundary in the ADS case, the asymptotic boundary is where you can think of where the CFT lives. And in this case, the asymptotic boundary is also a p-adic line. So you can think of as if the p-adic CFT lives also at the boundary of this graph. So we have to, very much like usual ADS-CFT, you have to put a cutoff in the asymptotic boundary for any calculation. And and if you cut it off, there would be dangling legs. So you have to decide what to do with the dangling legs. And so yes.
Boundary, can I understand this boundary as a state of CFT or not?
Very, very good. This is a state, as we're going to see when we generalize it to real CFT, we will use a very similar tactic. But this is not a state in the CFT. It is a state in a higher dimensional theory. You can see that we're not looking into the correlation we're looking into the partition function of, in this case, a 0 plus 1 dimensional theory. And but the way this 0 plus 1 dimensional correlation function shows up is as if we are looking at the wave function of a 1 plus 1 dimensional theory. So the tensor network appears to be giving the wave function of a 1 plus 1 dimensional theory, and you take the overlap of this 1 plus 1 dimensional theory with some direct product state, and it gives you the correlation function of a 0 plus 1 dimensional theory. And very surprisingly, this picture, even though we're talking about p-adic CFT here, the picture that shows up here is going to work when we want to talk about 1 plus 1 dimensional and in fact high dimensional real CFTs. So this is the point that I'm trying to convey. I'm very glad you asked this question. This Einstein equation business is only a digression, because I haven't and I don't know if I ever would get to the point that I'm able to read off also Einstein equation in the holographic tensor networks for these real CFTs that we're building. But what is for sure is that the picture that I just described, the overlap, which is why we talk about strange correlators, the overlap of some 1 plus 1 dimensional wave function with some tensor product state would somehow give you a partition function. And the question for real CFTs in 1 plus 1 dimensional or higher is to ask, what is this wave function that plays the role of this bulk tensor network that we talk about in p-adic CFTs. Does that somewhat answer your question?
Yes, thank you. Can I ask one more question? So where does your bulk field phi live in this tensor network?
Right, very well. So as I mentioned, when we built the tensor network, we had in mind to reproduce everything in the p-adic CFT. So a priori, I don't know what is bulk fields at all. But in the process of computing these 2-point functions of the p-adic CFT, as I mentioned, some geodesic got swept out, and the geodesic is such that every edge gives some contribution in a very specific way determined by the weight I put on the legs and also on the explicit values that I put on the vertices. And that value that contributes from this geodesic that is swept out corresponds to the solution of a Klein-Gordon equation on this graph with a very specific mass. The Klein-Gordon equation is the equation describing a Gaussian scalar field theory on this graph with a certain mass that is related to the conformal dimension of the CFT primaries in exactly the same way that you would expect of ADS bulk scalar fields related to boundary CFT primaries. And so because the answer tells us that it is a solution to a Klein-Gordon equation on this graph, that tells us that the bulk is secretly encoding a scalar field theory. And we can read off the mass of this scalar field theory in the bulk from the construction of this tensor network. And that matches with the proposal of p-adic ADS CFT in Gubser and friends, where he proposed that a Gaussian massive scalar field theory that lives on this graph should be corresponding to a scalar primary of a p-adic CFT. Now we don't have an action, but by constructing a tensor network that by construction reproduce everything in the CFT, it automatically tells you that this tensor network encodes a bulk fields with certain mass. And the result is such that the 2-point function came from the Green's function of on this graph, that set this Green's function of a Klein-Gordon equation on this graph. So that is something that emerged from this network by carefully choosing vertices such that this tensor network by construction recovers the CFT correlation functions to all points. Thank you very much for these questions. They are great. So this is just an advertisement that in the case of p-adic CFT, by perturbing a little bit away from conformal fixed point in the boundary conditions, and asking if it is possible to construct an Einstein tensor and a stress tensor such that they add together to become zero, you will find that the coefficients that I put here, these unknown coefficients, are over constrained by the infinite number of boundaries that I can put in, because these j's that I can put in, I don't necessarily require translation invariance, so it could be arbitrary at the boundary. So I get an infinite number of constraints, but then the expansion, as an expansion of this edge distance, it is a finite expansion with a finite number of coefficients. If I require that it has certain locality and symmetric properties on this tensor network. And so quite remarkably, my postdoc and I and our students showed that there's exactly one solution to these unknown coefficients, and they tell us that the Einstein tensor would reproduce some known mathematical results of Einstein tensor on this graph, and moreover, the edge distance on that is assigned to each edge, we took it as an expansion we took this edge distance as an expansion of the boundary data. And when the dust settles, we find that this edge distance is in fact a Fisher information metric that you can define on this network. Basically, it corresponds to the overlap of the Fisher information metric between two wave functions, one wave function with one extra line insertion here, and the other wave function corresponds to having a link inserted at the other vertex. And the Fisher information metric between these two wave functions would reproduce the unique distance assignment that such that the some kind of Einstein equation could actually exist on this graph. And so p-adic CFT can take you very far. So it seems that there is some success in constructing a tensor network that reproduce some very important features of the ADS-CFT correspondence quite effortlessly in the case of p-adic CFT. But of course, a p-adic CFT is not what we're really interested in. And so what we are really interested in is to construct holographic tensor networks that describe real CFTs. And what the lesson that we have learned from p-adic CFT, as I just mentioned following Hans' question, is that, first of all, the construction that we have is such that the CFT partition function takes the form of a so-called strange correlator. We have some bulk wave, the bulk tensor network looks like a wave function of one high dimension, a wave function of some one high dimensional theory, and then you take the overlap with some tensor product state, that gives you a CFT partition function. Moreover, the second point we learned is that this bulk tensor network behave like an RG operator. It looks like some kind of blocking process, and every vertex, as I mentioned, we take it to be the fusion coefficients of the CFT. For the p-adic CFT to make sense, the fusion coefficients have to be an associative, has to define an associative algebra. Therefore, we can ask, is there a generalization to associative algebra that takes the place of this vertex if we want to generalize this kind of holographic tensor network? There is, in fact, a very natural generalization, because an associative algebra is, you can also think of it as a so-called Frobenius algebra under suitable circumstance. And for Frobenius algebra defines a 2D TQFT, topological QFT. Therefore, it suggests very naturally that if I want to generalize this tensor network, maybe the bulk should be given by some higher dimensional TQFT. A generalization of a Frobenius algebra could be a fusion category or higher category, and maybe that would be a way to generalize this holographic tensor network to build up this wave function-like thing in arbitrary dimensions. And then the next task would be to look for appropriate boundary conditions to this tensor network so that I would recover a CFT one lower dimension. A CFT partition function one lower dimension. And how were these boundary conditions found? These boundary conditions that recover a CFT were such that, remember, they were fixed point of this tensor network. Every layer of these tensors, if you act upon the boundary conditions, you recover the same boundary condition that would be fed to the next layer of the tensor network. And therefore, it sounds like the recipe that we're going to follow is that, first of all, look for some generalization, some TQFT that is going to give, and their wave function would take the place of this holographic part. Look for, and then they define some kind of blocking the TQFT can define some kind of blocking process. Look for the fixed point of this blocking process, and that has that might give you a CFT partition function. The reason why I use the word might is because you might also get a TQFT rather than a CFT in one lower dimension, and so you have to find a way to distinguish TQFT from CFT solutions. Then we would be able to single out the CFT. But then how do we pick this TQFT? The answer to this question is that it is given by these new discoveries or new developments in categorical symmetry. For any given CFT with known topological symmetries, we know that these topological defects of the CFTs form a fusion category or some higher category if you are in higher dimensions beyond 1 + 1 dimensional CFT. In 1 + 1, these topological defects would be some topological lines, and they form a fusion category. And it was known that this fusion category would correspond to some 2 + 1 dimensional TQFT. So it sounds like the way to go is that this bulk should correspond to some TQFT, and we start with that TQFT, try to build some blocking operator out of this TQFT, and then from this blocking operator, look for fixed point boundary conditions, and that would be some kind of recipe to generate tensor networks that recover realistic CFTs. So we try to work with some realistic realizations, and the Levin-Wen model is one brilliant family of examples. And we were shocked to find that most of the ingredients were already on the market very recently. So how do you construct this tensor network out of the Levin-Wen model? So basically, it was observed in the literature that indeed the Levin-Wen model can be used to construct partition functions of minimum models. That is some observation that dates back to 2007 by Kitaev and collaborators, when they observed that you can construct CFT Hamiltonians, quantum Hamiltonians from the Levin-Wen model. And later, this observation was generalized into a very general method of constructing partition functions of minimal models. And this was done by two groups independently, Frank Verstreet and also Arson, Fentley, Mong, and company. What they observe is that, suppose I start with the wave function of a Levin-Wen model. The Levin-Wen model is a 2 + 1 dimensional theory, and therefore the wave function of a Levin-Wen model would be a 2-dimensional object. And then, if these authors found that it is possible to find appropriate boundary conditions, or in other words, some tensor product states, such that if you take the overlap between these 11-1 model and the tensor product states, you would recover the partition function of known integrable models. And if you tune these boundary conditions, you would be able to reach a critical point of these integrable models that corresponds to minimal models for 1 + 1 dimensional CFT. So now, starting from here, it is possible to construct a holographic tensor network. The way to go is that every of these 11-1 wave function has a very has a PEP tensor network representation. So these triangles corresponds to tensors, and by taking suitable choice of these triangles corresponding to the 6J symbols of the 11-1 model, this object and the physical degrees of freedom of the 11-1 model corresponds to these red legs, which form a hexagon lattice in this particular representation. So these red legs corresponds to physical legs of the 11-1 model, and by choosing these triangles to take the values of 6J symbols of the fusion category defining the 11-1 model, this would give you a tensor network representation of the ground state wave function of the 11-1 model on this lattice denoted by these red legs. Then, given these wave function, I have to project each of these legs, each of these physical legs to particular directions. That would give me a number, and that is the partition function of, that is going to be the partition function of the 1 + 1 dimensional CFT. Now, these triangles are 6J symbols of the fusion category. And so they satisfy a list of properties, particularly the pentagon relations. And therefore, it is possible to coarse grain these lattice that the 11-1 model resides. In particular, suppose you start with one lattice, you can do a recursive set of F moves. The 11-1 wave function, when I do certain F moves to change the lattice into some other lattice with a different lattice constant, the wave function would be the wave function on these different lattices are related by the 6J symbol. So when I convert this psi with lattice constant A to this psi with lattice constant Ka, this psi Ka would be related to psi A by a bunch of 6J symbols denoted by F here. And this thing can be done recursively. From psi Ka, I can go through psi K square A, and so on. And each time when I change the lattice, I would be multiplying it by further products of these 6J symbols F. Now, if you look into these 6J symbols, it would take the form of a mirror tensor network. So this series of F moves was also observed in these other papers, but it was never observed, or people did not appreciate that by this series of F moves, we are essentially constructing an analytic mirror type tensor network that takes a form that has the look of a discretization of a Euclidean ADS3, and by putting so this set of F moves is defining an RG operator, and if we're looking for critical points, then we're essentially looking for fixed points or eigenstates of these RG operators. And so this gives us a way of systematically looking for CFTs. So of course, the groups that came before, they look for CFT by comparing the results of these overlaps, and by tuning these omega, by clever choice of this omega, they realized that this takes the same form as known integrable models. So by comparing with known integrable models, they were able to fix the form of omega. But now it seems that using the RG operator, I could convert the question into one that asks, what do I do to look for fixed points of this RG operator so that I would recover a partition function of a CFT or a TQFT? So we went down that route somewhat. So we went down that route somewhat. As we're going to see, we generalized that story also to 0 plus 1 CFT and also 3 plus 1 CFT. So, but let me say a few more words about how did we use this knowledge to build up TQFT partition functions and CFT partition functions. So how do we practically do things with it? The thing is, it is actually very, very easy to look for all the topological fixed point of this RG operator defined by these F moves. And the fixed point of this RG operator is basically given by some Frobenius algebra object in the tensor in the on the fusion category. So these So Frobenius algebra object in a fusion category is basically certain collection of objects in this in the fusion category, such that you can define a product and a co-product, and this product and co-product together forms an associative algebra. And it is so by defining a product or co-product, it means that when I look into the fusion of different objects, I put in a weight of fusion. I can express the product and co-product in terms of a basis of fusion of the objects in the fusion category. And
Janet, can you hear us?
Yes, I could.
Oh yeah. Just to say, you have about 5 minutes left.
Okay, I'll hurry. Sorry about. So by picking this Frobenius algebra, it would automatically give you topological fixed point of this RG operator. So where are the CFT then? As soon as you identify all the topological fixed point, then the CFT is actually easy to identify because they correspond to phase transition points between these topological fixed points. And so this is somehow, this happens, we later realized that our observation actually matches with very recent paper of Xiaogang and his student back recently in May, that he came up with the proposal that it is possible perhaps to classify CFT by looking at phase transitions between a phase transition between topological fixed point, and each of this topological fixed point is characterized by some Frobenius algebra. So his language is somewhat different from ours, or there's some difference between input and output fusion category, and he was looking at output fusion category, but these languages are related, and in our explicit construction, it just emerges. It just emerges from looking for a fixed point of this RG operator. And so what is it good for? Can we actually do anything with actually finding fixed point? So we tested it. We tested this way of finding CFT using by looking for phase transition points between these topological fixed points. Namely, you have to parameterize the boundary conditions such that, let's say, it has a one parameter family that that you can tune, and then you throw it into the RG operator, allow it to be coarse grained by this RG operator, and it might either run. Then it would either spit out for you the it would spit out for you ultimately for a topological fixed point if you have fixed bond dimension in these boundary conditions. And then by tuning this parameter, you might either get one of the multiple different topological fixed points. And at certain couplings that you, as initial condition, you'll find that the RG operator would have more and more difficulty deciding which topological fixed point it goes to, and it would wander in some region for way longer before it falls into a topological fixed point, and that way we'll be able to decide the critical point of the CF. We would be able to determine of critical point, and for SU2 level K series of theories, we were able to use a just bond dimension of either 1 or 2 to immediately give critical values of these couplings to at least one significant figures when you compare to known theoretical values. We checked it for K equals 2 to 6. And just with very low bond dimension, bond dimension equals even just 1, you're able to get a significant one significant figures deciding where is the critical fixed point. We generalized this story to 3+1 dimensional bulk and 2+1 dimensional boundary, and in this case the TQFT would be some Z2. We pick a Z2 TQFT, Z2 toric code in 3+1 dimensions, and by choosing appropriate boundary conditions, it corresponds to a 2+1 Ising CFT. And using this method of throwing it into the RG operator and let it run to a topological fixed point, and let me add that the topological fixed point of 3+1 dimensional theory are also classified by higher Frobenius algebra. We have a recent paper about that with Liang, Kong, and collaborators, but this RG operator, and we were able to determine the transition temperature of the 2+1D Ising model by throwing into this RG operator, topological RG operator, up to one significant figure. With only bond dimension 1 for the boundary conditions, compared to values that we found in the literature, numerical values that we found in the literature. So this story also generalized to 0+1 dimensional theories and 1+1 dimensional bulk. We can classify all the boundary conditions that are fixed points, but in this case, it's not as interesting in the sense that a 0+1 dimensional theory, you don't really get any CFTs. So let me, I think I have run out of time. Let me just make one more remark. So this is some kind of holography that we are seeing here, some TQFT related to a CFT, but is this kind of holography really the same as ADS CFT? So it's unclear, but we made a simple computation and look into 2-point functions of a boundary insertion with a bulk insertion. And we find that these kind of 2-point functions, in the case of simple tensor networks that represent the Ising model, it looks actually okay close to a bulk boundary propagator. But within the numerical error, it is not conclusive. I can only say that it is not yet conclusive, but it is not completely clearly obvious that this is not possible. So let me just conclude here. So we have constructed some exact holographic tensor network that represents known CFTs, and we give out some practical ways of looking for boundary conditions that would correspond to critical points. And this somehow is related to an idea that was proposed by Song-Sik back in 2009, in which he observed that path integrals of d-dimensional field theory might be thought of as an overlap of two-wave functions in d+1 dimensions. One of the things that goes in there is a topological fixed point that is invariant under holographic, that is invariant under RG operation. So somehow our explicit realization here looks very intriguingly similar to the to this observation of Song-Sik, and the proposal that we have, or the family of tensor networks that we look at, have simple generalizations to high dimensions, and it is based on, you can think of it as based on the categorical symmetry of the CFT. You can go and look for appropriate bulk CFT, and then you go and look for appropriate RG fixed point or eigenstates of this RG operator that follows from, that gets spit out from the algebra operator that you build using the bulk TQFT. So it might be a way to generate more CFTs. So I hope that it is useful beyond talking about ADS CFT, and I also hope that it might have some implications on ADS CFT itself, but these are pure speculation. So let me end here. Thank you very much. Can you hear me?
Hello, Janet, can you hear my voice?
Yes, I could. Yes, now I could.
Okay, so there seems to be a microphone problem here. Janet, so we have the time for a few questions.
Sorry, I can't really hear the question.
So I will use my computer because there's a problem. So I'll just have one question, which is, so you have this network defined on this graph. What would you get if you put it on a regular tiling of, let's say, hyperbolic space of the Poincare disk that also is trivalent? Do you also get some CFT on the boundary? Is it p-adic? Is it something else?
Oh, sorry. Did you mean this tree graph when
right.
you
So
said
if you put a
trivalent
diffusion coefficients, but this time you don't pick this Bruhat-Titz graph. You would take some, let's say, some regular tiling of the Poincare disk, for example.
Okay, that's a very good question. I think the quick answer is we don't know, because there are lots of these tensor networks that people have studied before. For example, there's this famous happy paper of Harlow and collaborators where they studied a discretization of the Poincare disk, and they put in, let's say, perfect tensors on each of these vertex, and they were able to reproduce, let's say, the Ryu-Takanagi formula and many other aspects of the error correcting property of the bulk space, some of these properties. But one of the difficulty with these kinds of tensor networks is that it is by no means clear what is the boundary theory. And there is no way to tell what, and in those cases, they don't look like CFT, because in those cases, if you compute 2-point functions or 3-point functions, for example, low point functions, they would end up with being all disconnected correlation functions. There wouldn't be any connected components. So it is not completely clear what is the CFT that would correspond to a generic choice of tensors that you put into the tensor network, or some generic discretization. In this case, why do we choose the Bruhat-Titz tree? It really came from the fact that p-adic CFT, if you look at their conformal symmetry, that conformal group is completely preserved by this tree. So this is not an approximation that preserves some subgroup of the complete conformal group, as in the case of a discretization of ADS space. If I want to describe real CFT, then a discretization of ADS space would break a lot of the conformal symmetry. But in this case, when we choose this tree, it preserves the full conformal symmetry of the p-adic CFT, and therefore it is very.
Hello, I think you're muted, Janet. No, you're done? Okay, but yeah, that was very clear. Thanks very much. Are there any other questions? Hello?
Hello.
Oh,
sorry.
You're back.
Yes, I'm sorry. I'm sorry for all these technical.
No problem. It happens. It's okay. So William has a question.
Sorry, I kept clicking the wrong thing, and so I kept getting kicked out. Sorry about that.
Can you hear us now?
Yes, I can.
There's one question from William.
Okay. Hi, can you hear me, Janet?
Oh, sorry. Yes, please.
Yes, okay. So I had a question.
Yes, hi, Will. Yes, I can hear you.
Okay, good. So I had a question about the 4D Théorie code and its description in terms of a 2+1D criticalizing. So you went a bit fast. So I was confused about what's the physical picture of why you get the 2+1D criticalizing theory on the boundary. So that's my first question.
I see. So let me go quickly let me go to that first. So the way I know that I got the 2 plus 1D Ising was first by guessing. So the way it works is the following. When we looked into 2 plus 1 dimensional bulk and 1 plus 1 dimensional minimal models that was done in the literature, they give some boundary conditions to this level 1 wave function so that it matches with integrable model, known integrable model, the partition function of known integrable models. And we played with those things, and we realized that if I take the toric code wave function, the tensor network representation of the toric code wave function, which is also available, and we also constructed it independently, but it is also available quite recently. If we played with the tensor network representation of the 3 plus 1 dimensional toric code, and we realized that by certain choice of that boundary conditions, it would match with the known partition function of 2 plus 1 dimensional Ising model. Then we realized but then later we realized that we can also think of these 2 plus 1 dimensional Ising model as the phase transition point between the two different Frobenius algebra fixed points of the bulk tensor network. So we got to it through two different ways. First of all, we got to it by comparing with known partition function of the 2 plus 1 dimensional Ising model, and realized that by suitable choice of boundary conditions, they would match with each other. And then we returned to this problem by thinking about this point as a phase transition point between two topological boundary conditions to this tensor network, and the two topological boundary conditions were solved using these higher Frobenius algebra. But there is a very simple, rather than using these math terms, this Frobenius algebra, you can think of it as having electric charges condensing at this boundary, or magnetic charges condensing at this boundary. I guess this is not surprising. And the Ising CFT would come as a phase transition point between these two situations.
But in your first construction, when you're saying that this is the 3 plus 1D toric code wave function in a bulk, so are you saying that the 2 plus 1D critical Ising has a holographic description in terms of a higher dimensional TQFT?
Yes. Yes. I hope that. Yes. We're writing the paper. I hope that this would come out in 2 to 3 weeks. Hopefully not more than 3.
Okay, and so physically, is there a way to interpret the excitations of the 3 plus 1D toric code? So you have some loop excitations in terms of the boundary critical theory?
Oh, great.
That
they are the categorical symmetry of the 2 plus 1 Ising CFT.
So what is that? Say I don't know anything about category theory. What is the categorical symmetry of the Ising?
To call it the categorical symmetry, it just corresponds to recovering all the topological, I don't know if it is all, but it certainly is a subset of the topological defects of the Ising CFT. Topological defects are string operators and also membrane operators of the 2 plus 1 dimensional Ising CFT. And together they form a fusion category that is equivalent to the excitations of the Z2 3 plus 1 dimensional toric code.
And so these string operators, are they distinct from like a line integral of some primary in the Ising? Can you give an example of one of those string operators that you're considering, or that is described?
I don't really know how to describe it in terms of fields, but can I give an example in, let's say, it has an analog in 1 plus 1 dimensional Ising. So in 1 plus 1 dimensional Ising, you can find all the topological defects of the CFT, right? And they form, and those defects is also labeled by 1 sigma and psi. And this is something that you can construct explicitly, both on a lattice or or think of them as a continuous. Can I say that it is a continuous field? Maybe I could, but right. You can construct in a 1+1 dimensional Ising. You do have these topological defects, line defects.
So are you referring, for example, it's like insertions of two twist fields, or?
Right. The two twist fields, they are connected by a line, right? That line is topological. It is kind of fake. You can put it anywhere you wish, but it is. You can also think of it as a symmetry because it commutes locally with the Hamiltonian.
Mm-hmm.
Right, and those are the lines that I'm referring to. Yes. And the just one higher dimensional generalization of these lines.
Okay, well, I guess I'm looking forward to seeing your paper soon.
I would recommend looking into in the 1+1 dimensional case. I think Frank and Roger Arson Fendley, they had the reference that I showed where they talk about minimal models and Levin-Wham models. I think that is a brilliant exposition, and we learned a lot from it. And I think they did the groundbreaking work, and we are just doing a bit of we're just making a bit of progress on top of what they have already done there. So I strongly recommend their works on the subject.
Okay, thank you, Janet.
Any further questions?